where those. Okay. So now let's write this as matrix in terms of parity. Okay. So we'll figure out this. You should come on time. So let's figure out this as matrix in parity basis. Then we'll go to the how we can extract the different properties from this as matrix. Okay. So here, so if I am using the parity basis, so my ingoing waves, okay, so they are both even parity, even and odd parity, okay. Similarly, if I am having outgoing waves, so they are both what? Of even and odd parity. Clear? So previously we studied S matrix only in terms of the ingoing and outgoing waves in the asymptotic limit. Now we are considering the S matrix in terms of the parity basis. My states can be either having the even parity or they can be having odd parity. That means the ingoing states can be having either even parity or the odd parity, and the outgoing states can be having the same. Clear? So let me write these ingoing states. Okay. So let's write our ingoing states. So let me put them as the parity even. Okay. So let's write those as I means ingoing states. If I put I plus, so it means the parity, even parity. So how it would look like? So let me have let's say this is the potential or the scatter. When you are having ingoing waves, that means both waves are moving towards the scatter. So if I am having the even parity, let's say you are having this as e raised for I kx, left, okay. So right moving and this is the left moving. Okay, so it means it is having the parity even. So you sum them up. So let me put it like this in e raised power minus I k mod of x. Or you can write it in this fashion, or I plus x. So you can write it simply as e raised power I, linear combination of the two, plus e raised power minus I x. Clear? So do you think this is having parity one? When x tend, okay. So for x to minus x, this will become this state and this will become, so it is even parity. When x goes to minus x, so in the asymptotic limit, so you can be having either this state or that state. Clear? Got my point? When you take x tends to, okay, x to minus x, this is mod of minus x, that will be same. Clear? So this is the short representation of the same state. Clear? Okay, now let me write the parity odd. So parity odd ingoing states I minus x. So how I can write it? So that this is our scatter, this is an ingoing wave, these are two ingoing waves. So that means when I have to do parity odd, it means I have to take a linear combination with a negative sign in between. Clear? So I will choose a convention. So I'll put a minus sign on this side. Clear? So it means this minus this thing. Okay? So in other words, I will write a sine function, sine of x e raised power minus I k mod of x. Clear? So if I take x to minus x, this is positive, but it will change the sign. Clear? Got it? So that means this will be this thing under exchange of sign. Okay, or you can write it like this thing, I minus of x equal to minus e raised for I kx plus e raised for minus I kx. Clear? So these are the parity odd states, ingoing states. Now I have to construct the outgoing states as well. Okay, so let's write the outgoing states. Okay, so let's put the parity even. Okay, so let me write outgoing as O plus of x. So this is our scatter. Clear? So outgoing means like this. Clear? Okay, so what I will call this side? E raised power minus ikx. Good. So it is e raised for ikx. So this I can put simply e raised for, okay, minus ik mod of x. Okay, so I will put a plus here. Okay, so or this you can write as o plus of x simply as e raised for ikx plus e raised for simple linear combination. So this is simply the outgoing state. So this remember this diagram. These diagrams. Okay. So let's write the parity or. Okay. So let's write these are the outgoing states. So what I will do, I will write it as like this thing. So I'll put a minus sign on this side now. E raised for minus r. Yes. Linear combination of the two with a negative sign in between. Clear? So it will be minus sine of x e raised for I k mod of x, or you can write it as o minus of x as e raised for, okay, minus e raised for I k x. Sorry. So what it will be? Yes. Plus e raised for minus x. Clear? Okay, so now let's put them in a beautiful form, in the matrix form, these two. Okay. So let me write. So can I write this as, look here, you are having this I plus x and I minus x. So parity even and parity odd states. So I can write them in this fashion. In a matrix form. Okay. So can you tell me? So look here. So this is actually the right moving wave. So that is IR, and this is the left moving wave. So it is IL. So if I put 1, 1, minus 1 and 1. Now look here. So 1, it is IR, IL. What is our IR? So it is this thing. E raised for IX plus E raised for minus IX. Clear? So you know these things. So IR is what? E raised for IX, and IL is what? E raised for minus IX. Similarly, for the outgoing waves, you will be, okay, so let's write this as, let's define this matrix to be M. Okay, so I can write this as M. So this is a relation between, okay, so you don't have the parity states here. These are the parity states. Clear? Got it? Okay. So this is the relation. Similarly, I can write these O's. Okay. So I can write this O plus of X, O minus of X, same as M. Okay. O right moving. So this is the outgoing right moving. Clear? And this is the outgoing left moving. Clear? Got it? Samajh aa? Okay. So these are actually the relation between the right and left moving waves in terms of, okay, this is, okay, so this forms the relation for the parity even and parity odd in terms of the right and left moving waves. Got it? Okay. So let's put, so this is simply, I am defining, okay, we'll be looking deeply at these things from the examples. Okay, so now let's calculate what is our scattering matrix. We have not yet calculated the scattering matrix in the parity base. Okay, so let's try to figure out what our scattering matrix looks like in this parity basis. Okay, how I define this scattering matrix? Anybody? So we had a definition. You are having a right moving wave. Okay, so you are having a right moving, and then you are having this left moving wave. So you put it in terms of this thing, a right moving incoming wave and a left moving incoming wave plus a scattering matrix S, okay, OR, outgoing wave and outgoing left moving wave. Clear? So this was our definition of what? So S forms a scattering matrix. Clear? Now let's operate this equation by M. Okay, because we have seen a connection between these IR and IL, okay, with this M. Clear? So with the help of this m, I can construct these I plus and I minus. So now let's apply. Clear? So these are simply right moving waves and left moving waves having no parity, well defined parity. They can be any arbitrary parity. Clear? Okay, so let's apply this m. So I'll be having this psi r, psi l is equal to m I r I l plus ms, okay, o r o. Okay, so this object I call a psi plus a wave representing the even parity. Clear? So this gives you the wave in the asymptotic limit, is it? Okay, psi r is a right moving wave in the asymptotic limit. Clear? And psi l is a wave in the asymptotic limit. Clear? Containing both incoming and outgoing parts. So now this psi plus will give you the wave in the asymptotic limit containing both what? Even parity as well as, sorry, incoming even parity and outgoing even parity. Clear? So let's write this as psi l, psi minus. So plus means what? What plus means? Even parity state, and psi minus means odd parity. These are the states that you have in the asymptotic limit for from the potential. Okay, so what this is? So this is now incoming even parity state, and this will be incoming odd parity state. Clear? Got it? Okay, so here I will introduce, since this m, if you see, m is invertible. I can invert this m. Clear? So if it is invertible, it means its inverse exists. Got it? Okay. So I'll put like this in m, m inverse. So s, sorry, like this thing. M inverse m, that is identity O R. Clear? Okay, so what I get, so I'm having this thing, an even parity state and an odd parity state in the asymptotic limit. Okay, so in terms of the incoming and outgoing waves, so it's I plus, I minus. So here I'll write this as some SP. So this object I define as SP. Okay, P means parity. It is not power, it's a label, or it's a, okay, it is simply a label. Now what is this M O R O L? So it is O plus, so O plus and O minus. While we define this SP as M as M inverse. So this SP gives you the S matrix in parity basis. Clear? So this you can say, this forms the definition, okay, of an S matrix in the parity basis. If you know the parity eigenstates of the Schrodinger equation in the asymptotic limit, you can calculate the S matrix in the parity base. Clear? Got it? Any question? Okay. So now what this SP is? So you have to calculate what is M inverse and okay, M and M inverse and multiply it with S. Okay, what is our S? Anybody remembers? Yes? Okay, so I will write this thing SP. Okay, so you know the form of S, you know the form of M. So this SP is equal to T plus R prime by 2, R minus R prime by 2, R minus R prime by 2, T minus R plus R prime by 2. Clear? So this is the relation between the scattering matrix in the parity basis and the scattering matrix define it without parity basis. Got it? Everybody followed it? Okay. Okay, so this SP I define as, since it's a 2 by 2 matrix here. Okay, so I'm having only one scatterer. Clear? So it is only a 2 2 by 2 matrix. So this I write as S plus plus, one element, S plus minus, S minus plus, and S minus minus. So these are S plus plus means this very element, S plus minus the other element. Okay, got it? Okay. So now let me take the case. So we'll be only dealing with the even potentials. The potentials having the even this parity. Okay. So if I am having this very case, so when you are having potential symmetric, okay, about a given point, here it is about the origin. Okay, so in other words, you are having an even parity potential. Got it? Okay. So what will happen to the reflection coefficient? R and R prime, they are same. Okay. So in this case, you are having this R and R prime are this were shown in the last lecture. Clear? Okay. So when they are the same, what I am having? So therefore, this SP is simply equal to T plus R 0 0. So it is diagonal. Clear? So in other words, what you are having? So you are having S plus plus S T plus R and S minus minus. So why you are having this thing? Okay, so even potentials, when you are having a well-defined symmetry of the potential, it does not mix the even and odd parity states. Clear? So when you are having here R equal to R prime, so that is why you are having S plus plus and S, they are decoupled. Huh? So this is an independent of the other thing. Now if you look at this very equation, so if you are having, let's say, mixed parity, huh? Got it? So this is valid in general. Huh? Clear? So this kind of form, okay, here I have defined it only for the parity, in the parity basis. In general, you can be having an S matrix which are having all these terms non-zero. Clear? Whether the potential is having symmetry or not. Clear? So still you will be having all these four elements, they are non-zero. Got it? Only the property which is valid for an arbitrary potential, S has to be Hermitian. Clear? So no, sorry, S has to be unitary, not Hermitian. So when you are only the condition that is met, so S has to be what? Unitary. Clear? Because the probability, due to the probability conservation. Huh? Got it? Okay, so this can, okay, in general, if these elements are non-zero, these off diagonal terms are non-zero, that means there is a parity mixing between the states for an arbitrary kind of potential. Got it? Okay, so in that case, how to do the analysis? What you can do, you can simply diagonalize this very S matrix and okay, once you diagonalize it, then you are having only what? Diagonal terms. Got it? Okay, for even potential, I have actually diagonalized it. Okay, so diagonalization is here same due to the nature. This R and R prime are same. Clear? And it turned out to be diagonal. That means for the parity basis, this S matrix is diagonal. Got it? Yes. So it is automatically diagonal in the parity basis. But for arbitrary potential, it is not diagonal. You need to diagonalize it. Clear? Okay. Okay. So this, okay. So once you multiply M as M inverse, you will get this thing. So this is valid. Okay. So what I have used here, parity basis. But I have not figured out what potential is. You can choose any basis. Here I have chosen the parity basis. In the parity basis, this is valid. But if you are having any arbitrary basis, you can be having this S matrix as like this thing. Let's assume you are having only the two-dimensional 2 by 2 matrix. Clear? So it will be non-diagonal. You need to diagonalize it to extract information from this very matrix. Clear? Got it? But in case of the parity basis, if I choose the even potential, this automatically diagonalizes because this R and R prime are same. Off diagonal terms vanish and you will get only the diagonal terms. Got it? Okay. So okay, so now let's look at this very thing. So you are having this SP like this thing. Clear? So since it is a unitary, got it? So let me write it this way. So it is S plus plus 0 0 S. minus minus. That means there is no mixing between the parity states. Even and odd parity states exist independently. Clear? You can take a problem and solve it for even states separately and solve it for odd states separately. Got it? Okay, since it is unitary, so you are having like this thing as P dagger, that's equal to identity. What does that mean? So it means mod of, okay, so that's actually equal to 1 0 0 1. So it means mod of this thing equal to 1 and mod of s minus that's equal to 1. Suppose, okay, so this s plus plus can be in general a complex number, okay, because r and p are in general complex numbers, okay. So when you are having mod of a complex square equal to 1, what does it mean? So let's say if you are having mod of z square equal to 1, what does it mean? It means it's only a phase. Okay? So in other words, you can write, since you are having this very relation, z is equal to r e raised for I theta, the polar representation, when you are having mod of z square equal to, let's say it is r square, when this is equal to 1, so what it means? So it means it is simply equal to phase. Got it? So because of this unitary condition, these elements have to be only phases. Okay? In other words, they are simply numbers. So, samajh aawa? So, huh? Any question? Okay. So I can say so this implies s plus plus and s minus minus are phase. Okay, so let me characterize these things. Okay, so let me parameterize. Okay, so we parameterize these s plus plus and s minus minus in terms of phases, like this thing. So let me write this s plus plus. So since that is equal to r plus t, let me, since it is only the phase e raised for I phi, clear? So let me introduce that phase e raised for twice I. So this 2 is simply a factor, nothing you can put like this. Let me write delta plus k, clear? Got it? Plus means for the even parity, eh? Okay, so I will write this s minus minus as r minus t equal to e raised for twice I delta minus k. Why? Because this phase has to depend on the energy of the particle. Clear? Since r and t depends on what? They depend on k, the momentum. In other words, they depend on the energy. That's why these phases have to depend on what? Energies. I have put the argument of k here. Clear? So in other words, your scattering process is described by entirely by which phase? This delta plus and delta minus. Got it? So in a given scattering process, if you are able to figure out what these phases are, your scattering problem is done. Got it? Okay? So much now? So in other words, your scattering problem is reduced to merely finding these phases. Okay, so they will just give you the how the phase of an incoming wave changes. Okay, because of the scattering. Clear? Got it? Okay. So let's construct the bound states from these. Since we have done actually the scattering, huh? Okay, we have calculated. Okay, so we have already calculated this r plus t for a potential step. Clear? And we have calculated this r minus t for that potential step. In other words, we have calculated reflection probability and the transmission probability for a given potential. Huh? Okay, but what I want to do from this very formalism, I want to get the information about the bound states. Okay, so what does that mean? Let's say you are having a particle in a given potential. Okay, so in other words, we can think it as a scattering process. So this particle can be trapped by that very potential for some time. Clear? And ultimately it will move off. So this is also the possibility. Okay, so one possibility is that let's say a particle hits the scattered potential and within no time it goes. Okay? So that a typical scattering experiment. But it's also the possibility that this potential traps the particle. Okay? For a longer time. Okay? Let's say you are having an electron in the hydrogen atom. Clear? So it means the hydrogen potential has trapped the electron there. So and it is there, it is stable always. You can think this itself as a scattering process, but the scattering has yielded actually a bound state. Clear? Okay, so there can be one more possibility. Let's say the particle is trapped within the potential, it rests there for some time and ultimately tunnels out of the potential. Okay, so you are having three cases now. The usual scattering, a formation of a bound state, and a formation of an unstable state. Sometimes we call those as metastable states, where the particle is partially within the potential and ultimately tunnels out. Okay, so these metastable states exist as well. We call those as resonance. Okay, so let's try to. We have done the scattering. Okay, we have calculated this. Okay, this mod of r square and mod of t square for a given potential. I have given the example. Now let's try to understand the bound state. Okay, from this very scatter. This is very important. Understand the bound state. Okay, from this scattering matrix. Okay, so I will give you a simple example. I mean, although it is not simple, it's a non-trivial example. You know the formation of Cooper pairs? Okay, it's actually the scattering between two electrons at the Fermi surface, which are diametrically opposite to each other, having the, let's say, having the momentum that are opposite to each other, such that conservation of momentum is there. Okay, so it's simply a scattering process, but that scattering process yields you what? A bound state, formation of a bound state that you call as a Cooper pair. Clear? So you can get the extract information of that very Cooper pair if you know the scattering matrix of the problem. Got it? You can calculate what is the energy of that bound state from the scattering matrix itself. Okay? So let's try to understand it. Okay? Okay, so we look at the bound states which are localized near the potential. Okay? So what I will do, in order to figure out these bound states, what we will do, so we will simply make an analytic continuation to the complex plane. Okay? So remember this thing. So let's say you are having this K which describes your energy of the particle. Okay? If you remember this K, we have actually this thing twice mv by extra square. So this is your momentum vector. So you are having E as energy. Clear? So this case forms your energy. What I will do if I know the scattering matrix, clear? So I will complexify this K. I will take this K to some, let's say, I lambda. I will make it purely imaginary. Got it? Okay? So any strangeness? Huh? Okay? Any strangeness? What I am doing? Okay, so let's say, do you think there is any strangeness? Yes, it is a strange thing. I am making energy complex, is it? Do you think if I take K to be complex, I am making energy actually complex, is it? So is it strange? Taking K to complex, it's very strange, is it? Okay, let's look at the Schrodinger equation. What does that say? When we are looking at the solution of the Schrodinger equation, we have not constrained the momentum vector. Okay? So if you are having e raised for I kx as the solution of the Schrodinger equation, it equally means e raised for, let's say, e raised for minus kx is also the solution without I. Clear? So that does not mean, okay, so if your solution has k, let's say, purely real, that is a solution of the Schrodinger equation, it implies if you make k complex, that's also what? A solution of the Schrodinger equation. That means Schrodinger equation has no problem at all. Clear? So why the problem exists? Clear? So we need to figure out. Let's say, okay, so what is, okay, so why is the problem? Let's say this is the solution. E raised power minus I kx is the solution in one of the asymptotic regions. Clear? Got it? I am complex, I am making this k complex. Clear? Summation, what does it mean? So if I use k equal to I lambda, what it means is e raised power It will be simply lambda x. It means it is normalizable. The solutions cannot be normalizable. Okay, so you can take certain solutions can be normalizable and another cannot be normalizable. Let's say if you take x tends to plus infinity, because this is a which way it is. It's x plus infinity domain. Clear? Got it? Okay, so if you take x tends to plus infinity, this diverges. Clear? So this makes it non-normalizable. Although this is also the non-normalizable, there is no problem. It's a plane wave. Clear? So, but if you look at in the other region, x tends to minus infinity, it becomes normalizable. Clear? Samajh Shivan? So let's say if I make this k complex number, purely imaginary number, it means in certain domain I can figure out a solution which is normalizable. Let's say I am starting with a non-normalizable solution. Since e raised power plus minus I kx, they are non-normalizable. Is it clear? So you cannot normalize plane waves in the infinite domain. Only in the small domain you can normalize them. Clear? So what happens? Let's say if you make k imaginary. So what it means? So you are trying to make certain possible solutions, non-normalizable solutions, to be normalizable. When I am making a solution normalizable, what does that mean? It is a bound state, because bound states correspond to normalizable solutions. Got it? So in other words, tuning. So I should get an information about the bound state. If I tune my k, let's say to be purely imaginary. Okay, so I should get what? A bound state notion from a problem. Clear? So let's do it, mathematically. Okay, so we will assume a symmetric potential. Clear? So this is the assumption I will make because it makes things easier. Okay, so I will assume this v of x to be v of minus x, so that there is no mixing of parities. Okay, so let's take the even parity state. So I am having this psi plus of x in the asymptotic limit. Okay, so let me take the even parity state. So what it is? So it is I plus of x plus s plus plus o plus of x. Clear? Is it? Just from the S matrix definition. So you are having psi plus psi minus is equal to I plus I minus then S acting on that O plus and O minus. So you take the first case. I am taking only the even parity state. Other would be odd parity state. Clear? So how it looks like? So it looks like this thing. What is I plus? E raised for I kx plus S plus plus. What is O plus? E raised for minus I kx. What is the domain? Minus infinity. So what this is? E raised for minus I kx plus S plus plus E raised for I kx. X tends to plus. Got it? So it is clear? Is it clear or not? Okay, good. So now let's do it. What I was saying. Okay, so let me put this k equal to I lambda. That means I am making k purely imaginary. Okay. So then we'll interpret everything. Okay. So let's put it here. So what I will get? This psi plus of x. So if I put it, so first will be e raised for minus lambda x there plus s plus plus e raised for lambda x. What is the domain? X tends to minus infinity and it will be e raised for again lambda x plus s plus plus e raised for minus lambda x. X tends to plus it. Okay. Now look here. When x tends to minus infinity, which term actually diverges? This term diverges. Is it? When x tends to minus infinity, this goes to infinity. But if you look at this thing, it goes to 0. Clear? So that means this is a normalizable part. Clear? Similarly, if I look here, so this is actually the normalizable part and this is non-normalizable part. Okay? So what to do? Okay, so what I want to do, I want to make my wave function to be normalizable because I need to figure out what? The bound state of the problem. Is it? Got it? So, okay, so remember this thing. We are trying to figure out the bound state. It means my solution should be normalizable. And everything is scattering states here. Only I have changed my perspective from real plane to the imaginary plane. Clear? Okay. So what I will do, since this S plus, okay, so what I need to do, to make this part to be normalizable, this should go to 0. Clear? Is that true? And to make this normalizable, this should go to 0. Clear? So that my solution is well defined in a given region. So what I will do, since this S plus plus is a purely phase, okay, and okay, so this S plus plus, if you see, so it is simply e raised power twice I delta plus k. So it means for a fixed value of k, so this delta plus is fixed, is it? So in other words, this S plus plus is simply a number for a fixed value of k. Clear? Okay, what I will do, so I will divide this equation throughout by S plus plus. Got it? Since it's a phase and my solutions originally what I started with, they are non-normalizable. It does not mean, okay, it does not matter whether if you are having a non-normalizable solution, you divide them by a constant, so they still have the same property. Clear? Okay, so what I will do, so let's divide it. So I can write it as psi plus of x, so that I can write as like this, s plus plus inverse e raised power minus lambda x. Okay, so it is the inverse of this thing, this element, plus e raised power lambda x. Okay, x tends to minus infinity, and you are having s plus plus inverse e raised power lambda x plus s, sorry, e raised power minus. Clear? Got it? Any problem? What I have done? I have simply divided by s plus plus, and it's a number. Right? Dividing by a number, dividing a non-normalizable wave by a number does not change anything. Okay, it keeps it same because it's completely non-normalizable. Okay, so there is now a trick. So now I want what? Normalizable solution. What I want then? So this coefficient, okay, so this should be going to 0. If I make this coefficient to be 0, so it means this part goes to 0. So similarly here, if I make this coefficient 0, this part goes to 0, and I am having what? No. Okay, I am having a normalizable state. It means I am having a bound state. Got it? So when it will go to 0? So tell me. So if this s plus plus, okay, goes to infinity, if s plus plus diverges, what does that mean? So it implies actually what? S inverse plus plus goes to 0. Got it? So if it goes like this thing, what I am having? So the first term goes to 0, second term as well goes to 0. So I am having a normalizable solution. Okay? So if this goes to 0, when it is possible, it goes to infinity for k is equal to I lambda. Got it? Samajh aa? Okay, then I am having this psi plus of x is normalizable. Implies a got it? So when this will go to 0, so this goes to infinity, it means if there exists any divergence, a pole in this s plus plus. Okay, so if you are having a function, if it is having a pole, so it means it goes to infinity, it diverges. Clear? So in other words, what I need to figure out for a bound state, if you need to figure out a bound state in a given problem, if you know the scattering matrix for that problem, you only need to figure out what are the poles of the S matrix. Clear? So in other words, we need to figure out the poles of the S matrix in which plane? Complex plane. On purely on the imaginary line. Okay? So it means we have to figure out poles of S matrix on imaginary line. Okay. Suppose now, since you have complexified this thing, let's say this is your k plane. Okay. So this is your real of k, and this is plainly imaginary of k. So the bound states will occur on this thing. So any pole on this in the upper half of this very plane will give you what? A bound state. Got it? But if you are hanging them in the lower half plane, so we'll see in a moment what does that mean. Okay? So this analysis you can equally do for S minus minus. Got it? For the odd parity states. Okay? Samajh aaga? Any question? Okay, so let's take an example. We know the finite one potential. Clear? So let's take our cartoon again. So we know it's scattering. We have done it's scattering. Clear? Okay. So any question? Okay. So what is our S plus plus here? In this case, this we have already done. That's actually that R plus T, if you remember. So we have calculated R plus T as minus e raised power minus I k a q times tan of q a by 2, okay, minus I k divided by q tan of q a by 2 plus I k. This we have already calculated in the last lecture. Now you see, okay, forget about this factor. Numerator is complex conjugate of the denominator. So it's a phase. I have told you S plus plus is a phase, purely phase. So when you are having Z by Z star, so that means it's a phase. Clear? So now what I need to look. So this is a scattering matrix, R plus T, is it? So I need to figure out its poles. Where? Okay, before doing that, so we need to look at the energy, what we have done. So we had this K equal to I lambda, is it? So what is our energy? H square K square by 2m. Is that true? So let's put that. So K is, it is simply minus H square lambda square by 2m. So that is less than 0. Okay, so we have considered the potentials that vanish at the boundary. Huh? Okay. So that's why our E is less than 0. Clear? So now what I need to do? Just give me the prescription. So first what I have to do? No, first I have to figure out the poles. Where? In the complex plane. How I have to do that? I have to take K tends to I lambda. Got it? That means K tends to I K. Okay, so first what I will do? Let's take K goes to I lambda and find poles. So when is that possible? So you are having this S plus plus. So let me take K equal to I lambda. So that's equal to e raised power when you are having I lambda. So it is simply lambda A. Clear? So it is Q tan of Q A by 2. Let me write it for you people. So it is plus lambda divided by Q tan of Q A by 2 minus lambda. Clear? So where are the poles of this very function? When the denominator goes to 0. So poles are Q tan of QA by 2 is equal to lambda. So this is your transcendental equation. So what was our Q here? So in this very equation, so this Q square was equal to twice mv naught by h square plus k square. Clear? So what will be Q here? So you are having now Q square is equal to, so k square is what? I lambda, that's minus lambda square. So I'll put simply Q square plus lambda square is equal to twice mv naught by h square. Clear? So now you are having two equations which will describe me the bound state. How you do? It's a transcendental equation. Clear? So you need to solve them simultaneously. Clear? So let's say if you are having x is equal to tan of x. So you plot first tan of x, then on the same grid plot y is equal to tan. So y is equal to x, and look at where the two solutions cut. Clear? So let me give you the flavor of that. You have already done this in your previous semester. So let me give you the flavor to how to solve it. Okay. So first let me simplify it, because you are having lambda on this side, okay, and q here, q multiplied by this thing. I want it in this fashion. So I want this equation in this fashion, simply. Okay, so this is very easy to solve. Okay, so what I will do, I will simply make certain adjustments. Okay, so let me define. If anybody has not done this problem anytime solving a potential step, just look at the graph. So it is a problem there. It is nicely done in that book. So let me write this z is equal to some. Okay, so let's say qa by 2. So let me write this qa by 2 as z, and let's say you are having this z naught is equal to a by h cross root of mv naught by. Okay, so I'm using z naught. This actually it is here mv naught by h cross. So let's write it. So what is our z square? So let's write z square is equal to q square a square by 4. Clear? So similarly, you are having this z naught square. What it will be? A square mv naught by twice h cross square. Clear? So now let's figure out what is the relation. That relation, lambda square plus q square. So it means lambda square plus q square, that's equal to twice m by h cross square v naught. It implies your lambda. Just take q on the other side. So it is lambda is equal to root of twice m v naught by h cross square minus q square. Now what I will do, I will multiply this simply by a by 2. So in other words, so you multiply it by a by 2. When you take it in the root, so it will be a square. So it will be something a square mv naught by twice h cross. Clear? Got it? Okay. So in other words, you can write it like this: lambda a by 2 is equal to root of z naught square minus z square. This will be the form. Just multiplied by a by 2. So when you take it within the root, it will be a square by 4. So and use this z square and z naught square. Clear? Okay. So now let's use it here. So which implies you are having, okay, q. So you are having lambda here. Okay, from this very equation, what you get, so it is qa by 2, tan of qa by 2 is z is equal to lambda a by 2. What is qa? Qa by 2 is z. So it is z tan of z. So this object is z naught square by minus z square. So I will take z out. It will be simply z naught by z whole square minus 1. So what you are having ultimately, you are having this equation. So this is the transcendental equation. So you need to solve this equation. Okay, so let me draw. So this is simply, redefining the variables in terms of z and z naught. So that it becomes simple. Okay. Okay, so what I will do, first I will take this y is equal to tan of z. So let's plot it. Okay, got it? So you know tan of z is 0 at z equal to 0, and it's infinity where? At z equal to pi by 2. Clear? So let's take pi by 2 point. Okay, so this is your pi by 2, and this is 3 pi by 2. Okay, let's say this is your 5 pi by 2. So what this object is? It is z. So the argument is z. So this is your function y. So y. So how I will write it? So it is something like this. Okay, so this is pi here. So because at pi it will be 0, so it is some like this. So what it is? It is 2 pi. So it will be some. So I am not good at drawing. So you can just check the graphs of 10. Got it? So it is roughly like this. Clear? So these curves are what? So this, okay, so this thing and this thing. So they are simply your tan of z. So on this grid, now I will plot what? Y is equal to, so the other part, root of z naught by z whole square minus 1. So when you see, when z goes to 0, so at this very point it diverges. Clear? So you have to plot, since z naught is fixed, huh? Okay, this is a number, it's fixed. So only you change z. So it is something like, so this is the graph. Let's see. So at some point, I am not good at drawing something. Let's say at this point, z equal to z naught. It meets the axis. Okay, so now, okay, so this is your y is equal to this thing, this very object. So you are having a intersection here, and intersection here. So they give you actually the bound states. Clear? So they give you your the allowed states in the problem. Got it? Okay, so I have shown here only at the 3 points. Clear? Now, if you see, let's say if this z naught, if your potential is deep enough, clear? So let's say if your v naught tends to infinity, what does it mean? So you are making a potential well. Got it? So when v naught tends to infinity, it means this z naught becomes very large. Got it? So it means this z at very large values at the infinity, it becomes 0, touches the axis. What does it mean? So you are having infinitely many possible bound states. Got it? For a potential well, how many bound states are there? Infinitely many bound states. And where they will meet? If you see, when z naught tends to infinity, or in other words v naught tends to infinity, these points are actually very close to pi by 2, 3 pi by 2 and 5 pi by 2, because these will be very near to the axis. So in this case, this z equal to zn will be approximately equal to n pi by 2, where n is odd. N is 1, 3, 5, because it has to be pi by 2. Clear? So when you calculate the energy will turn out to be like this thing. Okay, n square, same thing, pi square, extra square by twice m, but 2a. 2a is the width of what? Potential. Clear? So this will be simply, this is what you are having the potential there. Clear? Now if this v naught tends to 0, that means the potential becomes shallow. Okay, so that means this z intersects this. Okay, so z intersects for the values of z. Okay, for a pure number of okay, when this v naught is, okay, let's say if this v naught tends to 0, that means it's a shallow potential. So what happens? Only the pure values of z, okay, will exist there. So let's assume there are only these three. That means when there are only pure points where there is an intersection, it means only pure number of bound states exist. Okay, when this v naught completely becomes to 0 or near to 0, there will be only one possible bound state. Only in one case it will touch this axis. Clear? So it will be, in that case, it will be something like this. Okay, when v naught tends to 0. So it is not exactly equal to 0, but only one, okay, bound state at least will exist. So that bound state will be having only parity even. Why? Because if you are having only one bound, okay, let's say if you are having a states, okay, many states in a given problem, the ground state is always what? And parity even state. Okay, for a parity even potential, it is what? Parity even states, and the first extent is parity odd. But if you are having only one bound state existing, it should be what? A parity even. And parity odd states will go. So this is how we calculate the bound states from this potential. I mean, from this very formalism. Got it? Okay. So let me give another quick example. How much time is it? Okay. So let's start.